Periodicity. Chemistry core subject. The periodic table, a very interesting table to be looked upon. It has a lot of elements in it. The elements are divided into metals, non-metals, as well as the divider metalloids. The metalloids are deployed in a diagonal line which divides the metals from the non-metals. Now, of course, there are also groups in the periodic table of elements. The main groups consist of group 1 through 2 as well as group 13 through 18. There are also transitional groups which is filled with transitional metals from group 3 through group 11. Of course, that's not it. There are also blocks. The periodic table of elements is divided into 4 blocks, which are the S block, P block, the D block, as well as the F block. The S block consists of group 1 and 2 as well as helium added. P block consists of group 13 through 18 with helium removed. The D block consists of group 3 through 12 with the addition of La and Ac and the removal of Ce through Lu as well as the removal of Th through Lr. The F block is filled with Ce to Lu as well as Th to Lr. The periodic table is also consisted of lanthanoids and actinoids. They are usually the two tables that is separated from the main periodic table. They are man-made elements. Now, of course, they are between group 3 and 12. Lanthanoids are La to Lu. Actinoids are Ac to Lr. The trends of the periodic table of elements. There are a bunch of trends, one of which is the atomic radii, or the radius of the atoms. The trend for this is throughout the periodic table of elements, when you go from left to right throughout the periodic table of elements, it decreases. However, when you go from the upper side to the downside, it's gonna increase. The ionization energy is basically the flip side. It's gonna increase from the left side to the right side and decrease from the upside to the downside of the periodic table of elements. There are more trends than this, one of which is electron affinity. The electron affinity trend is very interesting because it's not clear and it's different for every group. However, there is a trend for each group. There is also the trend for electron negativity, which is basically the same trend as the ionization energy. By the meaning of the same trend, it follows the movements in the direction of the trend, which is decreasing when it goes down the group and increasing as it goes down the period. The last trend is the metallic character of the element. This follows the same trend as the atomic radius or the atomic radii trend, which is basically it's gonna increase going down the group and decrease going down the period. And now for the HL topics.
The periodic trend applies to elements in the main group, or group A. The trends are different for the elements that are in group D. The elements in the group D are usually called as transition elements. All of the D block elements are transition elements with the exception of zinc, so their physical properties are generally the same. Generally, the groups in block D have high electrical and thermal conductivity, high melting point, they are malleable, easily reshaped or bent under the pressure without breaking the bonds. They also have high tensile strength, they can hold large load without breaking. They are also ductile, which means that they are easily drawn into wires. An interesting trait of a transition element is that they usually have more than one oxidation number. As shown in this table, every single one of these elements have more than one oxidation number. The most common would be iron, or Fe. It has 1, 2, 3, 4, 5 oxidation number, but the most common one would be +2 and +3. The reason for having more than one oxidation number is due to the nature of the elements in block D, which has electrons that are closer together because of the d orbitals being so close to the s orbitals. The electrons are removed without having a huge jump in energy. One example of this would be titanium. As you can see, titanium has a 3d orbital and a 4s orbital. This means that losing the 4s orbital electrons and losing the 3d electrons will be the same, because they would not require as much energy as, say, taking from the 3p orbital. So if we take the electrons from the 4s2s, then we would have Ti plus 2. And if we take the electrons from the 3d, it will still be the same because titanium has more than one oxidation state and it would not require a lot more energy than taking the electrons from the 4s2s. Another important thing when talking about transitional elements are ligands. Ligands are species with lone pairs of electrons that form coordinate covalent bonds to central metal ions. Interestingly, these ligands can only bond with transitional metals and they will form complex ions. An example of a complex ion would be FeCN6. Through this ion, we can identify that the ligand is Cn. which has 6 lone pairs bonded to the metal ion, also called coordination number. It has an octahedral shape and it has a charge of -3. The bonding of this complex ion is made possible by coordinate bonding. A coordinate bonding is when a bond is constructed by a pair of electrons that originates from the same atom. So one atom basically gives out a pair of electrons that will be used to bond with each other, whilst the other electron will just receive. But why doesn't this type of bonding happen in a normal metal? Ligands will give its electrons to an empty d subshell for bonding to form a complex. Normal metal does not have a d subshell, and therefore cannot engage in coordinate bonding with a ligand. Transition elements or transition metals have many usage in daily life. One example would be having it as a catalyst. Transition metals are often used as catalysts in chemical reactions. Here are some examples of reactions that you may be familiar. The first one would be Haber process. Haber process is a reaction that gives out ammonia. The catalyst used is a transitional metal, which is iron. The second one would be contact process. The catalyst used for this is vanadium oxide, or V2O5. The third one is nickel. Nickel can be used for multiple processes, but all of them is a process of hydrogenation. Manganese oxide is used as a catalyst for the decomposition of hydrogen peroxide. This concludes our explanation for periodicity. Thank you for watching.